Today we're going to start out with a brief review of energy, work, and power. Energy is simply described as the object's ability to do work. So it's looking at what the object has within itself in order to be able to perform some type of action. And we're going to be talking about what exactly work is here in just a bit. But essentially we're looking at an object's ability to change its inertia. So if an object's moving, can it move faster or slower? And how will need energy to make that change happen. Or if an object is resting, how do I get that object into motion? And again, I'm going to need energy to make that change happen. Energy is measured in the units of joules, which is notated by a capital J at the end of the number. And it's also important to recognize that energy is a scalar quantity, meaning that it does not depend on direction or the pathway that the object takes. This makes it nice to work with energy because we can simply look at what happened at the beginning of the problem and then skip all the way to the end, and the rules of our energy have to hold true regardless of the path that the object took in between. So if I talked about a roller coaster, my roller coaster could do all kinds of crazy stuff as it goes, or it could just be a little kiddie roller coaster. And when I'm looking at my comparisons, as long as I know this information up at that very beginning of my roller coaster, then I'll be able to figure out information for the very end of it because our energy does not depend on the path that it's taken. For this course, we focused on mechanical energy, and mechanical energy is the energy needed for an object to perform different types of motion. When we're talking about mechanical energy, it's the sum or the total of the kinetic energy and the potential energy. And there can be multiple types of kinetic and potential energy. We'll look at exactly what those definitions are here in just a second. But all the kinetic energies that I have need to stay the same. That's not to say that the individual energies never change, but if, for say, my kinetic energy were to rise, then my potential energy would have to fall in order to keep that mechanical energy the same. So our kinetic and our potential energies generally show an inverse relationship in order to keep that constant mechanical energy. So let's take a look at what exactly we mean when we say kinetic and potential energies. So kinetic energy is the energy that is used when an object is actually in motion. With this, we're talking about, so we care about the mass of the object, and we care about how fast that object is going. Kinetic energy, just as part of its equation, has this 1/2 factor attached to it, and then that v squared. So this is the equation that we have here to look at. So when we think about this equation, we need to recognize that if an object were to have no mass, then we'd have no kinetic energy. And if we have no velocity, then we'd have no kinetic energy. So an object has to be moving, and it has to have mass in order to be considered to have kinetic energy. Because we're dealing with multiplication in the equation, we need to recognize that we have a direct relationship between our mass and our kinetic energy. So if we have more mass, then we have more kinetic energy. By the same measure, we're also multiplying by velocity. So if I have more velocity, I would also have more kinetic energy. So here we would say that our mass and our velocity are directly related to kinetic energy. The other thing we want to get when we look at the equation is the velocity has this square attached to it, which means that small changes in velocity will do a lot more than a small change in our mass. So for example, if I were to double the mass of my object, let's say I picked up a backpack as I was running, and so now I have more mass attached to me. That will mean that I have more kinetic energy, twice as much. If I tripled my mass, then I'd have 3 times as much kinetic energy. But when it comes to velocity, because that velocity is squared, what's really happening is I'm going to double my velocity, and then I need to square it. So 2 squared, or 2 times 2, means that I'm going to have 4 times as much kinetic energy simply by getting twice as fast. So changing my velocity will always impact my kinetic energy more than changing my mass because of that square factor. When we talk about potential energy, we're talking about the energy that is being stored up, waiting to be used for some action. We have different types of potential energy. Here we list gravitational potential energy and we list elastic potential energy. Gravitational potential energy is the energy that's stored because of gravity. So when something's high up in the air, gravity has the ability to make it fall down. So can gravity pull it down any further? So if I were to think about something that was at floor level, gravity is always going to be acting on it, but it's already as low as it can go. So my object at ground level would have no potential energy. On the other hand, if I look at something that's resting on the top of a cliff, I could say that this object has potential energy. Now part of this comes down to the point of view that we take, our reference point. So if I were to set my reference point as here, then I could say that relative to the top of this cliff, it has no potential energy. But if I were to set my reference point down here at the bottom, then now I have all this extra height, so I have potential energy. By the same measure, if I said that this green line was no potential energy and my object actually did fall, then when it gets down here, I would say that it has lost energy, or now it's gotten to some negative component of energy, and that would have had to be replaced with something else, like like a different type of potential energy, or kinetic energy, or work, or one of the things that we're discussing here today. So also looking at that equation, we can see that, again, we're only dealing with things that are being multiplied. So right off the bat, we recognize that there's going to be direct relationships between everything that's on this side and that potential energy. So if I have more mass, I would have more potential energy. If I get more height, I have more potential energy. Or if the gravitational acceleration on the planet were to get larger, then I'd again have more potential energy. So we still have those direct relationships. The other kind of potential energy that we mentioned in this course that we didn't do a whole lot of focus on was simply something called elastic potential. And elastic potential is, like it sounds, something that has elasticity, the ability to compress or to stretch out. So rubber band, springs, even rope can have some stretchy ability, and so the ability of that object to be deformed and then come back. So like squishing a tennis ball as it hits the ground, and then it wants to bounce back to its original shape. For this course, we really just took a cursory look at it and identified it as a type. We did not use any of the calculations that go along with it. That said, there is an equation for elastic potential energy that you can look up and learn about in other videos. So when you're trying to decide what kind of energies you have, simple questions that you want to ask yourself. So, is it moving? So if it's moving, I can ask myself, is it fast or is it slow? And that's going to tell me that I have kinetic energy. But if I say that yes, it's moving, then that means I have some amount of kinetic energy. Is it high? So is it high off the ground? Does it have the ability to fall any further? If I say yes to that question, then I have potential energy. It is possible for something to have both types of energy at the same time. So let's say that I took that ball that was on top of my cliff and now I let it fall. Well, it's in air. I still have the ability to fall a little more before I hit the ground. So I have potential energy. But that object is most definitely going to be moving with some velocity. And so being as I have that velocity, I also have kinetic energy. And so as it gets closer and closer to the ground, my kinetic energy is going to get bigger and bigger because my velocity is going up. And my potential energy is going to get smaller and smaller because that height is going down. Again, we talked about that inverse relationship between our kinetic and our potential energy on the average basis. I can also ask myself for elastic potential energy, is it deformed? Has its shape been changed? So if I've taken something and I've pushed it tighter together, is it going to want to spring back out to where it started? Or have I stretched something and it wants to shrink back to where it began? Once we've identified what kind of energy an object has, we can help ourselves by recognizing that there's a law of conservation of energy. And conservation always means that we're just saving or we're keeping that energy. So within this law, the total energy has to stay the same unless work is done. Again, there's that big word work again that we're going to have to talk about. So what is work and how will that affect our law? But we're still, again, I want to point out we're looking at the total amount of energy that we have. So if I add up the kinetic and the potential at any location, then it should equal back to that total amount. For example, I have this picture over here where I'm starting out and I'm at the top of a very high cliff. So because I'm high up in the air, I have potential energy. But I'm not moving, so I have no kinetic energy. As I ski down that hill, I'm going to get less and less height. So here, my height's going to have to be less than 100, and so my potential energy has gone down. Now, when I first began, 0 plus 50,000, we had a total of 50,000 units of energy, or joules of energy. So even now that I've skied down a little bit further, I have a smaller height, so maybe 70 or 80 meters tall. And I could do some math here in a second and see exactly what that is. But I've also gotten faster. My velocity is now going to be greater than 0. And so I've had to offset that change in height by my change in velocity. So if I look, I have 20,000 units of kinetic energy now and 30,000 units of potential energy. I still have a total of 50,000 units. If I continue to ski down that hill and I get down here, where now I'm much lower to the ground, my height is much smaller, so having that smaller height, I'm going to have a much larger velocity. Again, if I compare my kinetic and my potential energies, 35,000 plus 15,000, do a little bit of math, and I still have 50,000 joules of total mechanical energy. So even though I've changed my position and I've changed my height or my velocity, that total amount has to hold true. Now I'm going to rise back up. And as I rise back up, again I get back to that same 50,000. I'll also notice that because I'm at the exact same height, so it looks like in this case I was only about 60 meters in the air. So having the same height means that I have the same amount of potential energy at this location as I do at this location. If I have the same amount of potential energy, then obviously I'm going to have the same amount of kinetic energy in order to keep that mechanical energy conserved. And then when I finally finish my problem down here at the very end, I'm as low as I can go. I have no height, so I have no potential energy. But because I'm as low as I can go, I can also assume that this is the maximum velocity that I'll have, where now I have 50,000 joules of kinetic energy. But together, their sum is still going to be 50,000 joules. So I've gone from one type of energy to another type of energy, but I've kept that total consistent the whole time. And that's what this part of the law down here at the bottom is telling us. We transformed from one type of energy to another. So I went from potential energy, and I turned that into both potential and kinetic. And then we turned where the potential energy was the biggest one. And then we continued to move down that slope where we still had potential energy and kinetic energy, but now our kinetic energy was bigger because it was closer to the ground and going a little bit faster. Then we went back to our potential energy and our kinetic energy. Since we went back up the hill, our potential energy took hold. And then finally we finished with that kinetic energy only. And at every location we conserved, or we kept that total amount the same. A common equation that we use is recognizing that however much my potential energy changed, my kinetic energy had to change by the same amount. So if my potential energy decreased, my kinetic energy increased, or vice versa. So if we think about the equation for potential energy, which is mgh, our mass is not going to change as I'm going across the ski slope. Neither is the acceleration due to gravity, but my height did. So if I compare my height at the beginning to my height at any other location, I can find the change in my height, which will give me the change in my potential energy. When we think about the equation for kinetic energy, again, our mass isn't changing, but our velocity is something that can. So if I compare that final velocity to a velocity at another location, I can see how much my kinetic energy has changed. Looking at a little bit of algebra and math on both sides of these equations, so it will cancel out, and I can simplify this formula to say that gravity, the acceleration due to gravity times the change in my height will equal 1/2 of the change in each of those velocities squared. And this actually ends up starting to look like one of the kinematic equations that we covered at the very beginning of the year, where I can get rid of this 1/2 because I don't really like fractions and move it over to this side. So we had an equation at the beginning of the year that said that our final velocity minus our initial velocity was equal to 2g delta h, or the change in height. And so this really connects all that stuff from the beginning of the year with our kinematic equations. So now you've heard me say that word work a few times, and I kept saying that I was going to come back to it. So here's where we're really going to start to introduce that idea of work. Obviously, my one skier by themselves was able to change from one type of energy to another kind of energy. But what happens when we have more than one object? The law of conservation of energy still holds true. In the absence of work, the total energy has to be the same. So when work happens, what we're really going to be doing is transferring energy from one object or one system to another. What we mean by that is if I have my car over here and it's on top of a hill, it's going to start out with potential energy. And as it goes down that hill, we'll end up with, again, a little bit of both. And at the very bottom of that hill, we're going to have kinetic energy. So on its own, if that car was allowed to slide down the hill, it would just want to keep going forever and ever and ever. But looking at my picture here, there's this little box. And that box is going to get in the way. So when my car hits the box, some of its energy is going to be transferred to the box. So my car will slow down, but my box will speed up. And this is that balance of energies. However much energy my car loses, my box is going to have to gain. Also, because that box is there, we're probably going to have some amount of friction as well. So we're going to have forces happening over here. So when we collide with this box, this is going to be where we describe what we call work. We're losing or taking energy out of the car, and we're going to give it to the ground, and we can give it to the box itself. So we're separating out some of that energy for each. But if I added up all the individual components, I should still have the same total amount of energy that I began with up at the top of that hill. So just some key details of what we mean when we talk about work. So work is going to be caused when we have that transfer of energy from one object to another. So work is done when our energy changes, and that had to happen when we had a force acting within a certain amount of displacement. So we have our equation down here that work equals force times, and that delta reminds us that it's a displacement. So not the total distance, but the change in the distance. Because the force is going to be the thing that's causing that motion, it's important for us to recognize that the force has to act parallel to the displacement. They need to cause each other. And we'll look at some examples of what that means here in just a bit, but this is going to be a key aspect of that rule. Sometimes you'll see in formula charts and things that, especially the ones that deal with a lot of trig, so if my car was moving in that forward direction left to right, and my box was going to be pushing against it, applying that force, so they are parallel to each other. Because they're parallel to each other, like I said, sometimes you'll see the equation where it's got this cosine theta added when we're looking at angles. For the purposes of our course, we only dealt with parallel and perpendicular, so we didn't really need to deal much with our angles at this level. So because work is simply a change of energy, we're going from one amount of energy to another. And we know that energy is measured in joules. What this tells us is that our work is also going to be measured in joules. We can use these words largely interchangeably with each other. While there are some differences in their definitions, we are able to mathematically use one in place of the other with some algebra. So because work is the change of energy, if we think about our kinetic energy, that change is going to happen when our velocity changes. Or with the idea of potential energy, that change is happening when our height changes. Examples of energy. So we can have our changes in energy. We can have a positive change in energy or positive work when we increase that object's speed. So I'm adding energy from one object into another. This is most likely going to occur when well, it has to occur when our force pushes in the same direction as our displacement. So if my car is moving to the right and I step on the gas pedal, I'm going to get more force in that rightward direction. That's going to be what causes that increase in my velocity. On the flip side, if my force acts opposite, so I'm moving to the right and I step on the brakes, now I'm going to be feeling that force in the opposite direction, and that's going to cause my object to decrease its speed. So we would have negative work. I'm removing energy from that system. So my removing energy, I have negative work, and if I'm adding energy, I have positive work. Examples of when we would have zero work would be in the case of when the force does not cause the change. So what this usually is going to mean is that either my object was resting and it keeps resting, or I maintain that constant velocity because I don't have a force. And then the most tricky part of this is when our force acts perpendicular to the motion. So what does that mean? If I pick up a box, I'm holding it up, my force is directed upward. I did work to take that box from ground level and lift it. So I did work as I lifted it. But now, if I were to carry that box across the room, so I'm displacing it or moving it this way, I'm no longer doing work because I've already done the work to lift that box up. Now it's at the same level, its potential energy isn't changing. If I walk with a constant velocity, its velocity isn't changing. So my force and my displacement being perpendicular to each other, this force is not causing this displacement. So when they're perpendicular, we don't have work occurring.